Hello, folks. Good morning. Very excited to see you here today. Today, we have a special speaker who goes and has crossed the bridge from academia to corporate to startups. So please meet today. Our speaker for you today is Dr. Alex Khan. Alex is with a company called BQP. But of course, Alex has had a long journey before getting into BQP. So you'll learn today about BQP, but also learn about Alex's role in the past at University of Maryland in Q Lab. University of Maryland is one of the largest quantum hubs in the country, as well as this journey, getting engineering degrees from Purdue University, Kansas State, as well as Duke University, being certified in quantum, and today being recognized in the Quantum Daily as one of the top 126 advisors shaping the quantum computing industry. But to tell you more about what Alex does, especially as VP of Product Development at BQP, a startup that's really focused on quantum optimization, I'll hand it off to Alex. Alex, over to you.
All right. Hi, everyone. Just make sure that I'm audible.
Yes, perfect.
All right. Okay, very good. So yes, pleasure to be here. We've already been working with WISER for the last year and looking forward to the next year with different fellows and the challenges that we're going to put out there. So looking forward to collaborating with some and looking at the work that you're doing. So this presentation I'll start sharing is just a quick update about BQP and the work we're doing over here. All right. So BQP is based in the US. We have offices in the UK and India as well. Our founders' focus on starting BQP was solving highly intractable problems in CFD or computational fluid dynamics. Most of their effort, they're from the aerospace industry, and their focus was how can they solve CFD problems using quantum computers, or how can quantum computers be leveraged to help in making these complicated problems easier to solve. We all kind of know that quantum computers are still at the early stages. Some of their early use cases are in chemistry and optimization. So I would say that solving partial differential equations and simulation problems is one of the more challenging use cases of quantum computing, but that is the area that we are working in. We have collaborated with many companies in the quantum ecosystem, also with many universities and industry partners, because our goal is to take real world applications and then use quantum computers to solve them. I'm sure you all know we haven't figured out all the algorithms and we don't have all the solutions with quantum computers. That's what you guys are going to be doing here. We are looking for a lot of innovation, new techniques, new methods, new algorithms to solve these type of problems. So we know it's a progression and we are in it in a number of different ways. So we are looking at current, what we call quantum now solvers. So in other words, taking inspiration from quantum and using classical methods. So we have a quantum-inspired optimizer that uses just classical methods, but it's inspired from quantum gates. So it's a genetic algorithm that uses quantum gates to some extent. We are also doing machine learning with quantum, so quantum machine learning, and also with physics, so quantum-inspired, quantum-assisted, physics-informed neural networks. And then we're also solving the physics problems or the partial differential equation problems. And that can be through machine learning. It can be through various solvers, solving linear system of equations or any other type of simulation methods. So you can see some of the stuff is near term, some is being researched for next few years. And then we are also working on very cutting edge solutions, for example, hydrodynamic Schrodinger equation methods for CFD problems that to some extent they're just theoretical right now. And so we're researching that. We're working with superconducting qubits, ion traps, and also photonic systems. So again, the motivation here is that there are some problems that are for the industry. We want high accuracy, but they're very expensive. We want faster solutions, but then we have low accuracy. And then hopefully we want to see if quantum solutions can get us closer to higher accuracy at with less compute resources faster. So this is the evolution I was talking about, going from classical algorithms with HPC, so we can have products out there right now. Also, there's an opportunity to teach people about quantum. So by taking quantum-inspired ideas, we're kind of seeding those algorithms or concepts of gates, even if we're not fully using a quantum computer. And then the next work is using GPUs with quantum methods, and then hybrid variational quantum algorithms with GPUs, QPUs, and CPUs. This is a partial roadmap. We have, so I represent the quantum R&D area. The company has a product area which was working with the industry, and then in quantum R&D, we're looking at these different problems from quantum inspired, like I said, to physics AI, to linear equation solvers, quantum native, variational, then eventually fault tolerant in the future. So we're looking at all these different type of solutions, and they're all in different levels of progression in what we can do and what we can demo and what's theoretical versus what's practical and so on. I'm just going to give you a few examples and then wrap up or see if there's opportunity to ask questions or not. But so this is our physics-informed solver, optimization solver. So it's available in MATLAB and in Python. Instead of using Atom or some of the other optimizers, you can replace it with our quantum-inspired evolutionary optimizer. It works exactly the same way. You just have to switch the name in MATLAB or just use this. We've seen that in certain problems, it will get to the solution faster, or it will get to a lower cost eventually compared to other solvers. We are also looking at it to replace the optimizer used in variational quantum algorithms and also in machine learning. So there's a lot of work we've done with this with different industry partners, and there's also a lot of research that we're doing in this to improve it for quantum applications. So this is an example of the physics AI or physics and machine learning, and then also quantum physics and machine learning together. So here, instead of just having a classical neural network, we can replace some of the layers with a quantum layer, and we're looking at how that benefits certain solutions. So here, for example, we have a comparison of a quantum-assisted physics-informed neural network versus a classical neural network, and we can reduce the number of parameters with this method, and generally with the right amount of reduction in the parameters, you can also generalize the circuit as well. So that's what we're researching over here. We've seen good results. We've seen that in some cases we need less data for the training. In some cases, the quantum learns better, and definitely on a parameter perspective, it definitely uses less parameters. We've also have a physics-informed machine learning with orbital mechanics use case. Here we are able to propagate satellite faster and with relatively good accuracy. Here I've got some results where we did some transfer learning with a quantum-informed pin or quantum-assisted pin, and we got to a 45-meter deviation from a numerical propagator. So the advantage here is we're close to the actual numerical propagators, but we are 1,000, well, here it says 250, but we are 1,000 to 2,000 times faster depending on the number of satellites we're propagating. So we can, in bulk, very quickly propagate thousands of satellites within a second that a numerical propagator would obviously only be able to do a few. And this actually gets us into a lot of different areas in space domain awareness, orbital mechanics, conjunction analysis, maneuver detection. Here at the bottom, we have an example of maneuver detection where we were able to detect satellite doing maneuvers in geo orbit of just a few kilometers. So we're also looking at quantum-inspired linear solvers, which you might be familiar with tensor networks. So we use tensor networks, which is classical, to solve CFD problems. We are also doing uncertainty quantification. So we use quantum machine learning. We use quantum Monte Carlo, and we have demonstrated that we can get to the same level of accuracy or uncertainty or error faster with a quantum Monte Carlo than with classical. So with classical, you need to do more measurements or more samples, but with the quantum Monte Carlo, we can actually get to the same level of accuracy with less samples. So we're also researching this. We're going to probably have projects to improve on this algorithm. And we are now, we've been working with universities like University of Maryland to take some of their classical, in this case, lift profile of an airfoil and do the uncertainty quantification both classically and then with the quantum Monte Carlo. We have, I think, like I mentioned, we have linear solvers that we are working on. You all probably must be familiar with HHL as the ideal quantum linear solver algorithm. There's a variational version of it called VQLS. So we're using VQLS, where we have looked at a number of different other linear solvers or solvers that can solve partial differential equations. And we've also improved on it. So we have some that have our own algorithm. We've improved our data embedding. We've also worked with Classic on this. And I think we have a pretty industry leading VQLS solver right now. But we get limited results. Even with that, we get limited results. We want to go to larger matrices and more real world use cases. So for that, we are working with universities to figure out how can we improve on quantum linear solvers. All right. I don't know if you have time for questions, or I'll end the slideshow here.
Absolutely, we can get through questions.
Yes, we do have some questions already. So those of you that do have questions that you haven't asked, please go to the live questions channel in our Discord, and I will see what we can get to. So the first question that we have, what resources would you personally recommend for building a solid foundation in the topics you work on? And then they had suggestions of like textbooks, courses, tutorials, lecture series, etc.
I think I would start with just doing some searches on how to solve Navier-Stokes equations. There's a lot of YouTube videos, I'm sure there's good YouTube videos on Navier-Stokes equations and how to solve partial differential equations. That's the classical equations that we are working on. Now, then the question is, okay, how do we solve those using quantum computers? So there you can look at the HHL algorithm, the VQLS algorithm, hydrodynamic Schrodinger equation methods. There's a number of papers that have come out in that just recently. You can also look at the work that IQ is doing. They're also working in that area. So yeah.
All right, thank you. Next question. Your roadmap shows several quantum-inspired and hybrid quantum solvers. For the deployed quantum-inspired optimization product, what benchmark problem can you share where it outperformed the best classical optimization method, and by how much in runtime, solution quality, or cost?
I'm sure the other people in the company do have those benchmarks. I don't have them with me right now, but like I said, we have seen the quantum-inspired optimizer find better solutions. And we're also comparing, a lot of our benchmarks are against the genetic algorithm, so GA, and it has outperformed GA most of the time.
This is another one kind of on the same topic. As we have seen, several companies do use milestones and roadmaps with dates. According to the big experience in business that you have, how do companies handle the problem that milestones might not be reached in time or similar problems?
Well, I mean, milestones obviously, or these roadmaps obviously have risk in them. We are obviously predicting where we think the hardware is going to be, the trajectory of how these algorithms will evolve. So we take in a lot of those factors as we're building these roadmaps. I mean, we also have past history. The company's been there for 6 or 7 years. So, I mean, we have progressed and we know how to execute on our roadmaps. So there's some history behind that as well. I think if you're starting out with looking at building your own roadmap or what kind of work you can do or how far you can progress, I think it requires a good understanding of where the quantum computing ecosystem is going, how many qubits they have, which quantum computers you want to leverage, what would be the number of logical qubits they will have over the number of years. And then you have to look at what problem you're solving, get some early benchmarks and see how many qubits you will need and how much gate depth you will need to solve bigger problems. So when we are putting these roadmaps together, we're looking at all of these different things. And then, it's kind of an art and a science, right? You're trying to achieve something, but you're also relying on many other parties to be able to get you there as well.
This person has asked, can we use Berger's equation solver for any type of medium?
So Berger's equation is a simplified version of Navier-Stokes equation. We do use it a lot in our benchmarks. I think a lot of our classical or quantum-inspired solutions, definitely we solve Berger's equation with that. And then with VQLS and some of the native quantum algorithms, we are solving Berger's equation. They're just at smaller matrix sizes. And as we increase the matrix size, we don't get to the ideal solution. So it's limited on what you can do natively on a quantum computer. So even on quantum simulator. So when we are doing VQLS, we're using quantum simulator, and we run into barren plateaus also. So these are variational algorithms. They're using an optimizer. They get into barren plateaus as you increase the number of qubits. So yeah, it's very limited problems that we can solve on quantum, even on quantum simulators and actual quantum computers. It's even more limited and with errors. But that's where we're trying to, figure this out. And that's where we need help. So we are looking for students that are interested in this area. It's a combination of a lot of different disciplines, as you can probably gather. You have to kind of know, partial differential equations, kind of know the airspace industry. You have to understand optimization, understand linear solvers, and then quantum as well, and then which quantum computer you want to use. So it's exciting in that sense, but it's challenging also.
Well, so on that, we have somebody asking, how can students contribute to these problems? Essentially, you were saying you have students, you need them. So how can they get involved?
Yeah, I've had many undergraduate, master's, graduate level, and then PhD level interns that we have worked with. Everybody contributes, at their level. I'm not expecting an undergraduate to be contributing at a PhD level, but I've had undergraduates, very smart undergraduates from University of Maryland and other universities that have worked with us that have made contributions. They've taken a problem that I've given them or taken an idea that resonates with them, that they can understand. They've moved in that direction and solved those problems. And I would have thought that maybe you need a PhD to solve that, but undergraduates have solved those problems. So I think it doesn't matter what level you're at. It's more of how innovative you are and how much you can research and figure out. Yeah, we also want to give everyone a chance to work, learn, and grow in their knowledge. So, of course, part of joining the fellowship program at WISER or joining a company as an intern is to have the company help you to grow and help you to understand what this domain is and how all of the things interact. I mean, we just had a WISER PhD work with us, and of course, very smart, but the feedback we got was that we were able to really show a breadth of the real world problems we're solving. We worked on the photonic system, so going beyond the theory and that they had learned into real world problems and then actual quantum computing and the challenges there. So
we do have a few more minutes, so I have a few more questions that we can get to. What sort of uncertainty have you dealt with while using the hybrid quantum native uncertainty quantification solver? Sorry, that question was a little bit worded weird. Did I ask it in a way that makes sense?
So uncertainty in the hybrid quantum solvers?
Yes.
I mean, I'm just going to see what I can answer.
Sorry, I can ask a different question.
Yeah. Okay. So there's two. I mean, there's uncertainty in just solving any problem on a quantum computer. So I'm sure everyone knows that there's no 100% answer coming out of a quantum computer unless you have a perfect algorithm. So there's obviously uncertainty in all results that we get back from a quantum computer. These are not numerical, so we don't get an accurate answer. We get probabilities of different answers, and we hope that we can get to the best answer with the number of measurements that we're doing. If you're asking about the quantum Monte Carlo, where we are doing uncertainty quantification, that product actually runs on a quantum computer right now. We are able to, so we've theoretically proven that there are proofs that quantum uncertainty quantification requires less measurements. We've also shown that algorithm actually work on a quantum computer where, for example, INQ running on the quantum computer on Forte needs less measurements than if you were classically measuring the uncertainty. So, and also with IBM with the Q control, where you can suppress the errors or do some error mitigation, was also able to demonstrate that you need less number of measurements from the quantum computer, the actual hardware, than with if you're measuring classically.
All right. Well, we do have a few more questions, but I think we're now out of time. So I'm going to honor your time, Alex. Thank you so much for joining us. I have lots of people saying that they were really enjoying your talk, and we appreciate your participation.